Yeah, welcome back. See, let's continue understanding hybridization with few more examples. In the previous video, we have studied that hybridization in C2H6. In C2H6, the carbon undergone Sp3 hybridization. Now we are moving towards next example, that is C2H4. The IUPAC name can be ethene, or you can call it as ethylene. You can call it as. Now try to propose the Lewis structure or Kekulé structure to it. The Kekulé structure will be like this. Okay, the Kekulé structure will be like this. Ethylene. Okay. Now if you count, let us see this carbon. Again, like C2H6, here also both the carbons are in similar environment. Same kind of bonding. So if you determine the hybridization for one carbon, then the hybridization and rest of the things for other carbon also going to be same. Yes. Now look at this carbon. How many sigma bonds it is forming? Single bond always sigma. In this double bond, one sigma, another pi bond. And there is no lone pairs or any other electron pairs left on carbon. Now 3 sigma bonds. So the steric factor can be 3 sigma bonds plus number of lone pairs 0. So the number you are getting is 3. So remember, when you get this S value as a 3, it gives Sp2 hybridization. See, after these examples, I will give you a best method, or you can say best technique to determine the hybridization of any example. But simply don't bother about how I determined the hybridization here. Simply you can do it. Look at this carbon. This carbon is having how many sigma bonds? 3 sigma bonds. And any lone pairs? No lone pairs. So if there is 3 sigma bonds, to form that 3 sigma bonds, carbon must need 3 hybrid orbitals. And the hybridization which gives 3 hybrid orbitals is Sp2. Now try to understand what is Sp2 hybridization or something. See, carbon, the atomic number is 6. Now the outermost electronic configuration is 2s2, 2p2, the ground state configuration. Try to write the excited state configuration directly, excited state configuration. Now normally 2s2, 2p2. Now after excitation, 1 electron here. Yes, there is 4 valence electrons in carbon atom. 2s2, 2p2, I excited 1 electron. Now this 2s1, 2px1, this is 2s1, 2px1, 2py1 and 2pz1. So these are the pure atomic orbitals, 2s and 2p orbitals of the carbon atom, the central carbon atom, the valence shell, right? Now what happens? These atomic orbitals with nearly same energy are going to intermix to give hybrid orbitals. Now the question is, sir, how many atomic orbitals are going to intermix here? The answer is very simple. How many hybrid orbitals you want? We need 3 hybrid orbitals, sir, because there is 3 sigma bonds. Oh, if you want 3 hybrid orbitals, then 3 atomic orbitals must intermix. So you intermix this 1s atomic orbital with 2p orbitals. That can be 2px, 2py. When 3 atomic orbitals intermixes, how many hybrid orbitals you are getting? 3 hybrid orbitals I am getting. What is the name of each hybrid orbital? Sp2 hybrid. The name of the hybrid orbital is called Sp2. And the hybridization process is called Sp2 hybridization. Sp2 hybridization. The name of the hybrid orbital is called Sp2 hybrid orbital, and the whole process is called Sp3 hybridization. So 3 atomic orbitals intermixes to give 3. Then what is the speciality of this, sir? There is 3 atomic orbitals. After intermixing also you got 3 hybrid orbitals. What is the speciality, sir? See, here atomic orbitals are not equivalent. This is s orbital. Its shape, its geometry or its energy is very much different from the shape, geometry and everything about p orbital. These are not equivalent. Of course their energy is almost same, nearly same, but they are not same. Their energy is nearly same. But after intermixing, you got 3 hybrid orbitals and all the 3 are same in all respects. So 3 sp3 hybrid orbitals all are equivalent. So do remember all these things happening in which atom? The carbon atom, the central atom. So okay na, in the valency shell of the central atom these things are happening. So finally you got 3 hybrid orbitals. Then the next step is very important. Sir, what is the next step, sir? The next step is after the formation of 3 hybrid orbitals or whatever number of hybrid orbitals, those hybrid orbitals has to arranged in space. Those hybrid orbitals has to be oriented in space in such a way to have minimum repulsion between them. There is 3 hybrid orbitals. These 3 hybrid orbitals has to be arranged in space in such a way to have minimum repulsions between them. And do remember, when there is 3 orbitals, the geometry which gives minimum repulsion is trigonal planar. The geometry which gives minimum repulsion is trigonal planar. Okay? Trigonal planars. So when there is 3 atomic orbitals or 3 hybrid orbitals, okay, formed, the geometry which gives minimum repulsions is trigonal planar. Sir, why sir minimum repulsions? When there is minimum repulsions means minimum energy. When there is minimum energy, maximum stability. Now let us say this is the carbon we are talking about, and now this carbon has got 3 hybrid orbitals, and 3 hybrid orbitals has to be arranged in space in such a way to have minimum repulsion. In such a way, trigonal planar. One sp2, another sp2, another sp2. Okay? Yes. So this is one sp2, another sp2 and another sp2. Are you getting my point? Okay, the point is, are you able to observe this? This may looking on the blackboard like this maybe, but you have to imagine this is planar. All these 3 are planar, trigonally planar, triangularly planar. If you draw a imaginary lines from this point to this point, you can understand. Trigonal planar. All the sp2 hybrid orbitals are in one plane only. Okay, one plane only. And when they are intermixing during the process, how many electrons are involved? 3 atomic orbitals, each having 1 unpaired electron. Then after intermixing also, there is 3 hybrid orbitals with 1 unpaired electron. So this with unpaired electron, unpaired electron, unpaired electron. Yes. Okay. Now the point is, all the 3 sp2 hybrid orbitals are in one plane. Sir, which plane, sir? Which plane, sir? Are you able to identify that plane? See carefully. This s orbital is intermixing with the 2 p orbitals. These 2 p orbitals are present in which plane? XY plane. X-axis, let us say y-axis. See, left to right, imagine like that, okay. Left to right, x-axis. Back to front, y-axis. Then bottom to top, z-axis. And we just leave this 2pz orbital. So this remained free. This is not participating in hybridization, right? So only the p orbital present in the x-axis and the p orbital present on the y-axis. That means both the p orbitals which are present in the xy plane, they are only intermixing. So after intermixing also, these 3 fellows will be in the xy plane only, right? So this is xy plane. But one more thing, the pz is perpendicular to xy plane. The pz orbital is perpendicular to. So this unhybrid, What I mean by unhybrid? The atomic orbital which is not involved in hybridization. This unhybrid pz orbital is perpendicular to the plane of the hybrid orbitals. Are you understanding? So this is 2pz. This is atomic orbital, pure orbital. It is having one electron also. Are you able to understand this? Okay. Yes. Now that situation. Now I am drawing this here. Carbon with one sp2, another sp2, one more sp2. sp2 with unpaired electron, sp2 with unpaired electron, sp2 with unpaired electron. So this is in xy plane, and this is, I'll give a different color to it. This is unhybrid p orbital. This is 2pz. Let us say 2pz. Okay. This is the case with carbon, right? Now the next carbon also same situation. Then that carbon, next carbon. So sp2 of this carbon overlaps with the sp2 of this one. So both unpaired electrons now got shared similarly. sp2 with one unpaired electron, one unpaired electron. Now what is this bond? Let me complete this first. So this carbon is also having a 2pz. This carbon is also having a 2pz with unpaired electron. So this orange color orbital is unhybrid pure orbital, and all these white color fellows are hybrid orbitals, sp2 of one carbon overlapped with the sp2 of another carbon. So this is sp2 sigma bond. Single bond is always sigma, na? Now what happens? sp2 of one carbon, sp2 hybrid orbital containing unpaired electron, is overlapping with the 1s of hydrogen. 1s spherical, right? Hydrogen 1s1. Hydrogen with its 1s1. See, this is the electron of hydrogen, this is the electron of carbon. Now the 1s orbital of hydrogen's 1s orbital having one electron. I am pairing this. Okay. Now what are those bonds? So what is this bond, or any one? sp2 s bond. sp2 s sigma bond. Single bond is sigma only, no problem about it. Now after the formation of carbon sigma bond, then these two pz has to overlap sideways only, no other choice, sideways overlap. That means these two carbons has to be get close enough so that there is a common space between them. So I can show that on paper like this only. So this bond is pi bond. So don't consider this as one pi bond, this as one pi bond. This and this includes only one pi bond. This and this, these two overlaps gives to only one pi bond. Okay. So the carbon, can I show here? Yes. So this is the carbon sigma bond. This sigma bond is formed by the overlap of sp2 of one carbon with the sp2 of another carbon. And this is what? This is what sigma? sp2 of carbon overlap with the 1s of hydrogen. Similarly this also. sp2 of carbon overlap with the 1s. Okay. Now sir, what about the bond angles, sir? See all these bond angles. Shall I take next page? In the case of this trigonal planar carbon, trigonal planar geometry, trigonal planar, the bond angles are 120 degrees. Bond angle is 120 degrees. Okay. Yes. So this is about sp2 hybridization. So similarly, let's discuss one more example which gives sp hybridization, beryllium chloride, BeCl2, right? Now try to give the Lewis dot structure to it, Be1Cl, another Cl. Fine. Now beryllium, atomic number of beryllium is hydrogen, helium, lithium, beryllium 4. Then the outermost configuration 2s 2, 2p2, 2s2, 2p2, no, 2s2 only. I am going to write the excited state configuration directly, 2s2 only actually, ground state, but I am going to excite this, then this is. So this is 2s, then 2px, 2py, 2pz. So beryllium atomic number is 4, 1s2, 2s2, that is 2s2. Now, what kind of hybridization you expect here? What kind of? You know very well this is Lewis dot structure or Kekule structure. One sigma, one single bond means sigma only, 2 sigma bonds, no lone pair. 2 sigma bonds means 2 hybrid orbitals you need. The hybridization which gives 2 hybrid orbitals is sp hybridization. Okay? See, it's so simple. In the Kekule structure, beryllium is forming how many sigma bonds? 2 sigma bonds. Is there any lone pair? No lone pair. Okay. Only consider about sigma bonds. Okay. To form 2 sigma bonds, how many hybrid orbitals we need? 2. 2 sigma bonds means 2 overlaps. 2 overlaps means you need 2 hybrid orbitals. Now, what is that hybridization which gives 2 hybrid orbitals? Obviously, sp. See, after these examples, I am going to give you a best trick or best method to identify the hybridization of any molecule, any ion by just looking at the formula. Okay? But now I am explaining the particular examples to understand, to have a better understanding about the hybridization. Now, we need 2 sigma bonds. 2 sigma bonds means we need 2 hybrid orbitals, and the hybridization which gives 2 hybrid orbitals is s and p. I am going to intermix one s orbital with one p orbital. Okay, one s orbital and one p orbital. Yes, fine. Okay, fine. Now, what is that hybridization? sp hybridization. How many hybrid orbitals you are going to get? 2 hybrid orbitals. What is the speciality about them? All are equivalent. In the beginning, this atomic orbital may be different from that one regarding shape or energy or anything. They are nearly same, not same, nearly same. But here, the 2 sp hybrid orbitals are same in all respects. And of course, there is no unhybrid orbital or with empty electrons. So there is 2 unpaired electrons, both involved. Fine. Now, you got 2 hybrid orbitals. Then after this, what is the step? Do you remember I explained in the previous class? After this, these 2 hybrid orbitals has to be arranged in space in such a way to have minimum repulsions between them. When there is 2 hybrid orbitals, the arrangement which gives minimum repulsions is linear. Yes, for suppose this is the carbon. For suppose this is the carbon I am talking about. This is one sp hybrid orbital, 2 sp we are getting, one sp and another sp. When there is 2 hybrid orbitals, how far they can be arranged? What is the longest distance? What is the longest distance they can be arranged? Yes, this is not linear. Now, this is one sp hybrid orbital, this is another sp hybrid orbital. During intermixing, each atomic orbital is having one unpaired electron. Then after intermixing also, each will have one unpaired electron. Okay. Of course, this is on xy plane, let us say x-axis. This intermixing is happening on x-axis, and on y-axis and z-axis there are empty orbitals, but no use of them because they don't have any unpaired electron, and we don't need also, right? We need just 2 bonds, 2 atomic orbitals. Then what can be the bond angle? 180 degrees is the bond angle, right? What is the geometry? Linear geometry. Fine. Yes. Now taking that beryllium here, one sp hybrid orbital, another sp hybrid orbital, sp hybrid orbital with unpaired electron. Yes, I'll draw in the middle. Beryllium, one sp hybrid orbital, another sp hybrid orbital. Sp hybrid orbital with unpaired electron, sp with unpaired electron. Now this is the sp with unpaired electron, sp with unpaired electron. Now the case is, this beryllium has to form a bond with chlorine. That means there must be some atomic orbital from the side atom to overlap there must be some atomic orbital with unpaired electron in the side atom to overlap with the hybrid orbital of the central atom beryllium, right? See, do remember, hybridization only takes place in the case of central atom, not in the case of side atom. Now you know very well about chlorine. Chlorine outermost configuration, the chlorine entire configuration I am writing to 1s2, 2s2, 2p6, 3s2, 3p5. Now what about this 3p5? Write in box format. 1, 2, 3, 4, 5. Let us say this is 3px, 3py, 3pz. So the way I written, this 3pz has got unpaired electron. Now what happens? The 3pz of chlorine atom, this is about chlorine atom. The 3pz of chlorine atom, the 3pz orbital, atomic orbital, not hybrid orbital. The 3pz atomic orbital of chlorine with unpaired electron is going to overlap with the sp hybrid orbital of the beryllium. Simple. So this is the 3pz of chlorine. Chlorine 3pz with its unpaired electron, common space. Similarly, next. So 3pz of chlorine, 3pz of another chlorine with its unpaired electron. That's it. Then how simply I can represent beryllium? Single bond, chlorine, chlorine. The bond angle is yes. The bond angle is obviously 180 degrees. What kind of bond is this? sp of beryllium overlap with the p orbital of chlorine. sp sigma bond. Of course, sigma bond. Single bond is sigma bond. Both are of same type. Now the point is, what is the percentage of? See, I have taken this sp hybridization. In this sp hybridization, each atomic orbital, see, if I take sp hybrid orbital, it means in this in this hybrid orbital there is 50% s character, 50% p character. That means you can say 50% s character and 50% p character. That kind of question also you may get. The percentage of s character in the hybrid orbital, because these are not pure orbitals, they are hybridized, they are intermixed. These are pure atomic orbitals. Here 100% s character, 100% p character. But after intermixing, what happened? Equally intermixing. Na? Similarly, you can get this also. See what happens here. If you take one sp2 hybrid orbitals, one sp2 hybrid orbital is formed by the intermixing of 3, 1s, 2p. So obviously the percentage of s character here is, s percentage is equal to 33.33% and p percentage is 66.66 like this, yes. Okay. And in the case of sp3 hybridization, sp3, if the hybridization is sp3, there is 4 atoms. This one sp3 hybrid orbital is formed by intermixing one s orbital plus 3 p orbitals. Okay. Then how to calculate the percentage? Let us say one s orbital, number of s orbitals 1 divided by total number of orbitals 4. Okay. Then percentage means into 100. That gives you 25%. So 25%. So 25% s character. Rest of the 75% will be p character in the sp3 hybrid orbital. Okay? Yes. Note చేసుకున్నాను ఇవి చక్కగా.